Hello, everyone. My name is Craig, and I'm going to be your host for today's STK webinar on the advancements of multifunction radar in 11.6. Today, delivering the webinar is going to be Mohammed Syed. He's an AGI Systems Engineer. Behind me, we have Vineet Kochar, who's a Senior Systems Engineer. And then also in the room with me today, we have Haroon Rashid, who is our Senior Advisory Software Developer at AGI. Before I hand everything over to Mo, I just want to tell you that we encourage questions. So using the GoToWebinar window, there's a questions panel. If you type in your question on that screen, we will see it on our screens, and we will wait until the end and have Mo or Vineet answer those questions. So please be patient as we try to get to those at the end, but we're going to deliver the content first. All right, okay, without further ado, Mo, it's all yours.
Thanks, Craig. So yes, today is the webinar on the STK Radar Multifunction Radar enhancement, which is built upon the actual STK Radar framework. So before we really get into multifunction radar, which is a new capability that has been developed, I really do want to focus first on the basics of what radar in STK already encompasses to kind of give us a bit more of a context for the multifunction radar. As many folks know, what exactly radar is a radar system essentially sends out a specific amount of power towards an object. As it sends out a specific amount of power towards that object, what ends up happening is a little fraction of that power ends up coming back to the radar, and that is what it is detecting to determine if or if not there is some type of object in the air or object that is approaching the radar. Occasionally, you will have folks like the little green alien here who end up using the power signal for jamming. So basically, with radar and the whole radar system, you have some portions that are nulled so that, folks like here, like in the UFO, are not able to as easily jam our radar signal. Just kind of talking about how STK handles radar capabilities is it uses the dynamic physics engine that STK has to offer. It uses the object attitude dynamics, so depending on the orientation of, say, an aircraft, with a specific radar cross-section, you may or may not get better or worse results from the radar apparatus. Along with that, in STK, we do incorporate things like frequency, Doppler shift, and bandwidth overlap types of analyses. So that's building on top of that physics framework that is really in comms and radar, and it's been used for quite some time within STK. Along with that, we do have the jamming power computations that are able to be taken into account too with the radar. So we always want to make sure that not only is the radar able to visualize any specific platforms or detect any specific platforms, but also take into account any type of other radar signals that may be jamming our radar. So the performance analysis when it's under jamming or just in general is done at the receiving end of the radar to make sure that we are actually taking into account the proper jamming signals. And that is because sometimes you have multiple jammers, some of which may not even have any type of bandwidth overlap, and we want to make sure that we are ignoring the proper jammers and taking into account the calculations from the normal jammers as well. One thing within STK radar is also the ability to have either a uniform or a spectral power distribution model being used. So what that allows you to do is when you do have the power distribution model being used, you have a bit more increased fidelity, which means that you have a bit more increased calculation time. But along with that, you have a better idea of finding out what exactly is the shape of that signal as it's coming in. So like I was saying, of course, as we add more and more effects within STK, the fidelity of it will be increased, but so will the computation power. So you just have to make sure that your machines are able to handle that. Along with that, STK Radar also does include the effects that are incorporated from ground clutter reflections within the analyses, if you do so choose. So just continuing a little bit off of radar. So one thing is like I was saying, there's many different strategies for finding a way to deal with jammers that are affecting the radar. You have the different type of jammer signal types and RF transmission types that are being incorporated. And like I was saying before, you can include and compute that true jammer power that is seen by the radar. And you have different methodologies for reducing that jammer power into the radar receiver through the use of, say, spectrum filters or nulling of a phased array antenna. So if you remember, there was the example I was giving about the alien who was trying to jam our radar. With the use of something like phased array, you have the ability to just block the signal going in the direction of that entity so that you don't really have its jamming effects, or its jamming effects are minimized. So with an SDK, you also have the ability to make or to model dual channel radars. So these are the kinds of radars that will allow you to transmit a signal, the same signal at the same time, but you have a different polarization. So in this case, it could be like a primary or orthogonal polarization. So you could picture if you have a horizontal signal going out, you will also have a vertical signal going out, or along with that, a left-handed signal and a right-handed signal to going together. So depending on the different configurations you can have a whole different number of them. You can have one transmitter to one of the receivers, one transmitter to two of the receivers, 2 to 1, or 2 to 2. And the radar computes these signals, has the ability to compute these main signals and the leakage of these signals from one channel to the other channel. And that's through the use of complex scattering RCSs, or a block matrix. So each point in your RCS matrix is a complex 2x2 matrix, but that is needed to get these configurations right. One can also think of a dual channel radar as what some weather channel organizations use. They use what's called a WSR-88 weather radar. And the really big use of using a dual channel in these cases is not only it allows you to detect certain weather patterns that are coming in, but it allows you to determine what exactly the clouds are made up of. So you're able to determine, is this a snow system coming in, just a hail system, or a regular rainstorm? So with the dual channel, it does definitely give you a bit more fidelity that you wouldn't have otherwise. Continuing a bit further, within STK, and for a while within STK, we supported constant false alarm rates and PDIT algorithms. So the first two here, which we see as constant false alarm rate and non-constant false alarm rate. But along with that, we have recently added in the ability to do cell averaging CFAR and ordered statistics CFAR. So the advantages of using both cell averaging CFAR and ordered statistics CFAR is you basically can compute multiple cells behind and in front of your actual object. So what that allows you to do is it allows you to really increase the fidelity of what you are trying to calculate. So for example, if you would want to calculate about 16 different cells along with what your radar is trying to detect, 8 cells would be in front of your object, and 8 cells would be behind the object to make sure we're getting the entire swath. One big thing about STK, and it's included in more than just radar, is the ability also to give users access to their own algorithms through the use of plugins and other methodologies like that. That is because we know within STK that there are multiple things that come out of the box, such as these 4 different types of CFAR detection. But we also know that many users at different organizations have their own exotic algorithms that they would want to include within the radar capabilities and the calculations. So we definitely want to make sure that we give those metrics out and that ability out to users. Along with that, we have sensitivity time control. So the biggest reason to do sensitivity time control is it's to make sure that we attenuate the signal at the receiver so that it isn't overloaded with a whole bunch of noise or transmissions that it doesn't necessarily need to get from, say, things like clutter modeling. So with an SDK, just like I was mentioning for the CFAR detections or the CFAR algorithms, is that you can also supply your own algorithms into the sensitivity time control as well. Along with just algorithms or plugins that are more programmatically heavy, you can use base scripts. So you see here we have a SDC data mapping that includes range or elevation range and azimuth range. We have different documentation that tells you how exactly you need to formulate that file, which is very similar to how an antenna file is formatted within STK, which is used for radars as well as transmitters and receivers. Like I was mentioning, there are clutter models that STK can handle too. And when you have clutter models, the way STK handles it is it does it in really 2 steps. The first step is how it computes, or is to compute the geometry that will then be used for the second step, which is computing the reflection off of that geometry as you're going through the radar analysis. And once again, just like I said previously, we indeed include the user the ability to ingest in their own models, because not everything will be right out of the box of what the user is trying to do. Now we're going to jump into multifunction radars. Over time, with really technology in general, folks want more and more calculation power, more tasks done at once, such as the example of a computer processor. In the beginning, there was only 1 core, and eventually that wasn't good enough, where we then went to dual core, kept on going up and up to quad core, to 8 core, now we're seeing 12 core, and supercomputing is now a thing. Similarly, radars kind of went through that same kind of transformation. Initially, we would have a single channel radar, which was already done in STK, and a dual channel radar, which we discussed and also works in STK. But we've realized that we needed more than just 2 channels at most. We realized that in this new evolving world that we will have a multifunction radar or a multi-channel radar able to process tasks concurrently. So just like these modern processors, we now have multifunction radars, which have the ability to process multiple tasks at once. The nice thing is with multifunction radar is that your tasks are now able to be scheduled properly by radar operators such that each task or each beam or radar has a different start and stop time so that you can accomplish more in one time span. So, like I was saying, you can assign tasks to different beams, to the same beams, looking at similar things with different powers. It really, the point is that you have the flexibility to do so at your own whim. Like I was saying, multifunction radar with an STK is a multi-beam radar model. So currently within the multifunction radar, each beam that you model is in the form of a pencil beam. But what it's basically doing is it's our way of modeling a phased array at an abstract level per each beam. The beams can be single or dual channel when we were talking about the polarization, and each of the beam has its own independent search track performance analyses. So what this basically means is, when you're done setting up the story that you're trying to tell with an STK, with all your radars pointing at the proper direction, we now can then get the data metrics out for each one of those beams independently of one another, so you can see exactly what is going on. So here we just have a summary of a property panel of the multifunction radar, and you can see the different assortment of capabilities and parameters that you can change. As you can see at the top of the screen, we have the beams, pointing, location, transmitter receiver, jamming, clutter, and detection processing. Some of you folks who have used STK radar previously must be or are probably familiar with some of the tabs that you see here. Along with that, you can see each beam ID, the current frequency, power, gain, and so forth that are assigned with each. I'll be jumping into a little bit of each of those as we go on a little bit from now, including things like the pointing type. Currently, in multifunction radar, the current version supports a single array plane, and that array plane is fixed with respect to the parent object. So if you have a parent object and it's oriented as a ground system, or this is on some type of aircraft system, your array orientation will be basically fixed the way the orientation of many different platforms within STK is. Along with that, though, we have different other types of orientations that you can have, 3 to be exact. One of them is the fixed plane orientation. Another one is the ability to have spinning sensors. And the next one is to track different objects. And each of these beams, as you're going through this tracking, can be configured independently when it comes to the frequency, the power, and the waveform. Waveform is a collection of pulses, and the signal waveform can be defined at the beam level, so be it with the PRF and pulse width. Currently, the way waveforms is modeled within multifunction radar is it is a fixed value that is associated per each beam, but I will get more into that in a little bit, but that is probably going to be evolved in the future to accomplish and accommodate more needs that a user would have using the multifunction radar. And this is just a quick look at the waveform parameters as they are right now. As you can see, you have the ability to set the pulse definition, the wavelength, the pulse width. Many parameters that you would be familiar with is if you were using STK radar. So, we were talking about how the beams are now configured and they are assumed to be pencil beams. But along with that, here are the things that can be changed about each beam. So you have the ability to control the gain of the main lobe of each pencil beam, the beam width, and then the side lobe gain is computed using those values. And another thing, of course, is that beam pointing, which we were talking about. And this is just going back into the different types of pointing orientations that I was talking about when you're with respect to the radar. So like I was saying earlier, you have that fixed orientation, you have the targeted, so any platform that you have that's flying within the vicinity, traveling within the vicinity, you're able to have your multifunction radar point to it. And along with that, a spinning radar, as a specific spin rate of your choosing. So going back into one of the properties menus for the multifunction radar, here you can see that we have a very similar drop-down list to what is proliferated all throughout STK. On the left, we have available targets, which in this case is an aircraft with its own transmitter. Maybe that transmitter is a jamming signal. And we're able to then assign our multifunction radar's particular beam to that specific target, which in this case is the aircraft. When it comes to how the beam activity works within multifunction radar, not every beam will have to be active all the time or inactive all the time. Usually it's a combination of these that really make sure that you're managing your power and the rest of your resources correctly for the multifunction radar. So you have times and you have the ability to set a beam to be always active, which is just a constant beam, such as a spinning beam that you would want to have on the entire time. You have the ability to set it to inactive because you won't always necessarily have all your beams used in a specific scenario. You may be throwing in different objects to test with, so instead of having to delete that beam entirely, you just have the ability to set it to inactive to make it much easier from a usability standpoint. And then you have the following two. You have the collection of time components. So within STK, we have a sister module named Analysis Workbench, and this allows you to add different particular time components to the beam. And when I say time components, this means that we can add specific time periods where, say, an aircraft is within line of sight to your object. And we can use that unique time as an identifier of when you want your particular multifunction beam to point to it, such that if you start changing the route of that aircraft, the multifunction radar's beam will adjust accordingly to make sure that you're just always tracking without having to explicitly put in times. Along with that, though, you do have the ability to put in specific times through the use of collection time intervals. So you can add intervals where you will see specific times, such as t is equal to the start time of your scenario to, say, 10 minutes later, or you can ingest those explicit times from, once again, something like an analysis workbench component. And like I was saying, these time components could be based off a multitude of objects that you have in your scenario. So here's an example of a use case, and this is a pretty good use case of what a user would want to use multifunction radar for. So like we were saying, you can have the multifunction radar to target many different objects, and each of the beams in the multifunction radar is assigned to track different types of objects that you have within your scenario. So in this case, let's imagine that we have a multifunction radar with 6 beams, and each of its beams are designated to track 6 different objects in our STK scenario. These objects could be anything from a ground vehicle, an aircraft, a spacecraft, or a missile. So let's pretend it is a missile, and we have access to one of those missiles that is incoming. So through the use of the normal workflow with an STK, we have the ability to compute and use the data to determine which one of those beams that we are getting an SNR or PDEF for is able to best detect this missile while we're tracking it to its assigned object. So we have the ability to kind of play around and determine what is the most optimal situation, what is the most optimal beam to use for really any object coming in, depending on the orientation of the object, if it has a radar cross-section that is aspect dependent, the speed of the object, and the range. And we're not limited to those, of course, but those are just some of the examples that we have in this case. So when it comes to the computations, the performance analysis of the multifunction radar will be carried using each of the beams. Each beam will independently have its own type of calculation so that you're able to compare one beam to the rest of the beams. So it's not like you just have an overall value for the entire multifunction radar and you are not able to discern the metrics for each beam. We deliberately put that in to make sure that we can give users the entire list of data that they would need to make sure that they're getting the proper results that they're looking for. So, going into the beams, and more particular the power, the way the power is used within multifunction radar is, if you look on my screen, we have a main tab for the transmitter where we set a max power. So in blue here, you see that we have written that the sum of the power across all beams does not exceed the user-defined maximum power limit. So what you're seeing right here is the main transmitter tab, and we have a max power value. If you recall, there was a few slides back where I showed each of the beams listed, and they each had their own specific designated power. So at any specific time instance, the sum of the power of those beams cannot exceed this maximum power. So that doesn't mean that if we were to aggregate all of the beams in our list, that all of them would have to be below this maximum power. What it simply means is that at some certain time intervals, we'll have some beams that are off so that they aren't using the power at all. As long as at every instance in time we're below, in this case, 50 decibel watts, we will be fine. So this also can show you what is your power management and your ability to make sure that you're managing everything properly while still getting the results that you are looking for. We also know that not all radars will be able to see everything, or that maybe there are some tolerances that you would want to confirm and put on as constraints. So the constraints within a multifunction radar work almost in a global sense for the entire multifunction radar. So, for example, we can have things, constraint metrics such as single pulse SNR, integrated PDET, dwell time, and things of that nature. The thing is, though, is when you are computing the constraints, STK will take into account the metrics for the entire multifunction radar. So if at any point you say you want a maximum signal pulse SNR, it will apply that constraint to all of your beams. So that is definitely one thing that you will have to take into account. So they are set as the min-max constraints that you have in the regular SDK menus. So for example, if we look on screen, this is what we see as for a multifunction radar constraint. You can see here that we have the ability to set things like the single pulse SNR, signal pulse PDET, integrated PDET, things that you would see with just most of the things that you would see with a traditional single or dual channel radar. Along with that, we also have constraints that deal with the multifunction radar jamming. So not only can we set signals as if there were no jamming, but we know in most situations that there is some other type of signal that is deliberately out there trying to jam a multifunction radar. And through the use of these constraints, we now can once again tailor our measurements to make sure that we are within a certain threshold that is of acceptable value to our requirements. And this is just the use case that we have already seen, just kind of talking about the six objects. So now you can imagine, going back to this example, that now we can take it a step further. Now what if we add in jammers? What if along with a missile there was another object that was an aircraft with a specific jammer on it? So this is just kind of going back to show that, we are able to build on top of the multifunction radar to really get in as deep as we need to kind of play that game of, can our multifunction radar with its current specs accomplish the mission that we designed it to do? So here we just have a bit of images on the multifunction radar itself. So in this image, we're showing we have 4 beams, and in the corners we have data metrics for each of those beams. As you can see here in the top left, is the one I'm going to be focusing on, we have integrated SNR here in decibels that is listed. Up here at the top, we also have maximum power. As you can see here, we have a little data display that determines and tells us that our total beam power at this current instance in time is only 41.139 decibel watts, which is below the maximum power limit. So along with that, like I was saying, you would also have metrics such as jamming come in the way. So here we have a second screenshot, and what this screenshot is showing is it's showing a bit more data metrics that take into account how jamming is affecting it, which is, once again, something that you would see at a single or dual channel level using the STK radar module without multifunction capabilities. So just to highlight, you could see here that we have a search track integrated SNR of minus 55.6982 decibels. But we also have this metric here that shows us the signal to noise ratio, or S over N plus J. So the signal to noise ratio with jamming incorporated, which in this case is minus 79.9818 decibels. So recall that these are all using the installed physics with STK, as well as the physics built on top of that through the use of radar. So we're able to actually determine how our multifunction radar is doing with and without jamming, to determine if we need to use a stronger beam or go back to the drawing board and approach the problem in a totally different manner. So far, what I've been showing is just screenshots and just kind of going through the bulleted lists. But just kind of to put kind of a wrap on everything, I did want to show a video kind of going over some of the multifunction radar capabilities. So within this scenario here, we have a multifunction radar which has 4 beams on it. 1 beam is spinning, 1 beam is following an airliner, and 1 is pointed towards a fixed horizon. The 4th beam will come into play when a different airline or a different aircraft called the private plane comes within view. So this is using the combined knowledge that we just went over, where the 4th beam will only start tracking once it's within line of sight to the private plane. And this is through the use of time components. So I'm just going to go ahead and hit play here. As you can see, we're in an unmarked location, but we have our 3 beams. We have this one here in the back pointed towards our airliner, tracking the airliner. We have another beam that's pointed toward the horizon. That's the one in the middle here. And then the one on the left is the spinning one. Here's the properties menu for everything. As you can see here at the top, we have targeted spinning, And then the last two are fixed orientation and targeted. The time components are basically going over and saying that the horizon search, or the third beam, is going to be always pointing to the horizon when we don't see the private plane. And the fourth beam is pointing towards the private plane when it comes in view. So here we're playing, and if you look here at the bottom, I'm going to pause here real quick. You can see where my mouse is at the bottom. We have two different orange bars to really focus on. The one at the very bottom is the orange bar that corresponds to the time the private plane is not seen, and the second one is corresponding to the time that the private plane is seen. These also line up with how the beam behavior will work, where the beam that is pointing to the horizon is currently on because the bottom bar has orange in it, and then the tracking beam for the private plane will turn on right in this center section here. So let's go ahead and hit play. We have a spinning rate that's pretty quick, and you can see that we had a switch off here. And as soon as it switches back, we have the beam pointing right back at the horizon again. So I'm just going to go ahead and repeat that little section here for you one more time. And I'm just going to go ahead and hit play, just to reiterate and show it. So we have the beam spinning, and as we have one of the other beams pointing towards the airliner and another pointing towards the horizon. And we have that switch take place right there. So you can imagine now that both these beams that turn on and off, they could have the same power, and the aggregate of all four beams could possibly go above our power limit. But because the two beams, the one pointing towards the horizon and the one tracking the private plane, are not actually on at the same time, their power will never be exceeded. And you could see through this, now if I was to change the route of the private plane, that both of the beams, beam 3 and beam 4, will automatically adjust because they are tied to the availability of the private plane with respect to this ground location where this multifunction radar is. So really, just to wrap everything up here, just with popular demand of some of the things that we're looking for the future, currently the way waveforms are modeled within multifunction radar is that every single waveform is explicitly attached to a beam. So it's attached to a beam where it can't be changed, where in the future what we want to do is have a list of beams as well as a list of waveforms that really allow you to allocate the proper waveforms to the subselection of beams so that it's no longer locked in to one specific setting being one beam. And at every time step, that waveform will be dynamically assigned in such a way that is kind of based on how you would expect your waveforms to follow the beam behavior. And what we're really trying to shoot for with this is we're trying to shoot for an 11.7 release. So later this year, we will expect to have those kind of changes incorporated within STK as we go forward. Multifunction radar is a very complex kind of system here. So as we go into the future, we're planning to just add more and more capabilities to make sure that it accommodates all the needs that any user could possibly have.
All right, thank you. If you have questions, you go home and you start to think about this webinar, as I'm sure you will at the dinner table. You're like, man, I should have asked that question. You can always email us at info@agi.com. That is info@agi.com. We'll be happy to get back to you with any of those questions. We do have one that came in here. Can you localize jamming source and null, and what level at DSP analysis? And I'm probably going to ask Vineet to answer that one. Okay, actually, Haroon's going to answer this question, which is very exciting.
STK analysis actually do look into the positions, the range, and of course the attitudes of all the jammers in the scenario. So it does report where and when and how a jammer is impacting our radar system. So all that information is available in STK reports. Not only that, in case there are multiple jammers impacting a radar system, STK will then report on all of them, and you can actually see that which of those jammers is really impacting more than others.
Thanks, Haroon.
Thank you so much, Haroon.
We did record this webinar, and it will be available on our YouTube channel at youtube.com/analyticalgraphics. So stay tuned for that. Like, subscribe, whatever we need to do on YouTube. I think it's subscribe.
Subscribe and then hit that bell button so you get notifications of all the videos that we have posted.
Perfect. Thanks. So if there are any other questions coming in, send them in at info@agi.com, and we will get back to them and have the right engineer respond to them. Might be Mo.
Could be.
Might be Vineet.
Could be.
Could be Haroon. We don't know. But we'll task that out when the questions come in. Again, thanks for attending today, and hope to see you at that webinar or the virtual training on May 9th for Introduction to STK MFR, which is Multifunction Radar. So we're going to teach you how to use it on May 9th. Again, thanks again.